Okay, we're going to start by going through context-free grammars. So, a context-free language is a way of something we can represent using a context-free grammar, and this is a more powerful way of describing languages. So, regular expressions let us define any regular language, whereas context-free grammars, we can also define some irregular languages. So, a context-free grammar, here's an example of one. And we define it like this. So, we have different symbols, and we say those symbols are defined as something. So in this case, this A is defined as some terminal 3. This A is defined as some terminal 5. But we can also have recursive rules. So this A is defined as something else that's A plus something else that's A. And so we can derive strings in this grammar. So for example, if we said, say we had something like A, and we wanted to show that 3 is more than 5 plus 3 is in this grammar. So what we'd do is we'd say A can be 3, and then we can also, so we'll use this rule to say A becomes, actually, let's change this to this. Okay, so we can first use this rule down here to say B becomes bracket B bracket, and then this B can become this. So for example, it's a more than, so we've got more than, A is more than A. This we know is 3 because this is the left hand side of this more than, and then on the right hand side you have 5 plus 3. So this would become, this rule here would be A plus A, and this A is 3, this A is 5. So we can show that using this grammar we can derive this word, and so this word is in this language that's defined by this grammar. We can also write these rules in a more concise form. So, yeah, we can also write these rules in a more concise form. So if we see on the left here, so we have A is defined as 3, and this little line here just means or. So 3 or 5 or A plus A or A times A or brackets A or this if statement. And the same way we can define B. B is defined as some occurrence of some instance of A more than some instance of A, or B and B, so this is referring to itself, or it can just be B, but we can have brackets on either side of it. So the idea is we can define these rules, and these rules can also reference themselves from within themselves. And this lets us represent irregular languages, sorry. This little symbol here means this is our start symbol. So this whole grammar is represented by this grammar represents the language which can be derived from this start symbol here. So for example, if we had something like 4 here, so B maps to 4, 4 alone would not be derivable in this language because we don't have anything like this. 4 is not defined as a start symbol, as a rule in the start symbol. So we always want to make sure we're looking at that start symbol when we're deriving a word. Okay, so this sort of notation of writing a context-free grammar is called Bacchus-Naur form. A and B are called non-terminals because they're almost like variables which we're saying are defined as something else. Whereas the characters in sigma, so for example 3, 5, these are examples of terminal symbols. Every line with this little symbol here is called a production rule, so this whole thing represents a production. You might sometimes see it as a production rule. And this tells us how to replace a non-terminal with a string of terminals and non-terminals. And that's where that recursiveness comes in. Formally, a context-free grammar is a 4-tuple. So we define 4 things to have a context-free grammar. We need a finite set of variables or non-terminals. In this case, our non-terminals would be A and B. We need sigma, so this is all of our terminal symbols. In this case, this is 3 and 5. R is a finite set of rules or productions, with each rule consisting of a variable and a string of variables. So each of these rules would be in R. And finally, our start variable in our variable set. In this case, this would be A. And A is in this A comma B. Is a production rule just any rule that isn't the start symbol? It may also be, it consists of the start symbol as well, but it's just a set of all of these rules. So it will be something like A maps to 3, A maps to 5, and then all of the B ones as well. All of these will be in this set. Okay, so one thing I just want to clear up is I believe these would also be non-terminal. These would also be terminals. So the plus, the times, the brackets, and if, then, because these are all of the instances where they aren't referencing some other variable. We stop the, it's like the base case of recursion. So all of these would be examples of non-terminal symbols. Sorry, terminal symbols. Okay, so if we want to derive something, say we want to derive this, so we're trying to derive if 3 is more than 3 plus 5, then 3 else 5. We're trying to derive this with the grammar we had above. So we can say A maps to if B, then A else A. So we've replaced that. We said A equals, A maps to if B, then A else A. Okay, and then, let me copy this down actually. We'll get there. Oh wow, this is a lot of pages. Okay, found it. Right, so this is our grammar, and this is our derivation. So A can map to if B, then A else A, because of this rule here. And then we can replace this B. So this dot tells us what occurrence of a variable we're replacing. So then we can replace this A with a 3, with this. And we can replace this A with a 5. So we've done that here, and we've done that here. And then we want to replace this B with something. So we've replaced that with A is more than A, with this rule here. And then we've put the dot over the A. So we're going to replace that with a bracket A, a bracketed A. So that's what we've done there. All this dot is doing is it's saying we're using a production rule to replace that occurrence of a variable with something else. So then we replace this with a 3, replace this with this expanded A plus A, replace this with 5, and this with 3. And we can derive this string by following those rules in our Backus-Naur form grammar. Do we draw a derivation tree? We can draw a derivation tree. So that would probably be the easier way to do it. So this is how they've gone step by step to show exactly what we're doing. But if we want to draw a derivation tree out for this, we'd say A goes to if B, then A else A, and then this is a terminal, this is a terminal, and this is a terminal. So we just need to now look at these. So B went to A more than A just went to, so this second occurrence of an A just went to 3, this third one just went to 5. This A went to 3, this went to brackets, A brackets, and this A just went to A plus A, this went to 3, and this went to 5. Is there a reason we place a dot above the A? Yeah, so the dot's telling us what occurrence of a variable we're going to replace in the next step. So in the first step, we start with this, and we replace this A with this whole chunk here. And then we look at this here, and we replace that with a 3. Then we look at this and replace that with a 5. Then we look at this and replace that with this. So it tells us what occurrence of a variable we're going to replace in the next step. Specifically on the, so we just start by starting with whatever this start symbol is and expanding that into something, because that's always where you want to start when we're deriving something. Okay, so yeah, note the principles. We always begin with the start non-terminal. In this case, this is A. At each step, we replace the non-terminal indicated with a dot by a string of terminals and non-terminals, according to one of the production rules in this grammar. And at the end, we have the desired word in sigma star. The grammar is called a context-free grammar because we can apply a production to any non-terminal, regardless of any of the other symbols of the string. So we can look only at this A, And the way we derive this a if it was alone, and if it was something like this, is the exact same. We don't have any external context when we were deciding how we're going to derive that. We just look at the term we're deriving and look at the rule that would be useful to us. The set of strings that can be produced or generated from a grammar is known as the language of the grammar. We can write it like this, so language of some grammar G. And the language produced by a context-free grammar is known as a context-free language. Yeah, okay. So that's in terms of what this actually means, what Backus-Naur form means. Then we have different ways we can derive stuff. If they ask us to derive something, do we have to do the line-by-line method or the tree method? I'd probably say either is fine, yeah. As long as they can see what you've replaced with what. But if they ask us to do a leftmost or rightmost derivation, that's where we want to do it in a specific order. It's not too difficult. So if we have something like this, start symbol, the leftmost occurrence of a variable is just this variable here, this a. So we expand that into this. And then we just look at the leftmost occurrence of a variable again, in this case this b, and expand that. Then we always look at the leftmost occurrence again. So all we're doing is we're only expanding the leftmost occurrence of a variable until no variables remain. And we call this a leftmost derivation. Similarly, we can have a rightmost derivation. This is where we just expand whatever's on the right hand side. So this a first, then this a, then this b, then this a, then this a. Yeah, we don't need to know BNF specific. I think it would be good to understand how BNF works, because it's yeah, I'd probably, it's a type of context-free grammar, but this is like the method of context-free grammar that we're kind of studying, so I'd probably understand how those rules work, because then when it comes to our topic later on Chomsky normal, that's written as a BNF. It's just a subset of BNF. So, yeah. But yeah, this is leftmost and rightmost derivations. And all of these derivations, as said previously, can be written as a derivation tree like this. So A goes to this, then B goes to this. This A is a 3. This is a terminal symbol, so we don't need to expand this anymore. A goes to this, goes to this, goes to these two. And so all we're saying is what rules we can use to map A to our terminal symbols like this. So everything in the leaf nodes essentially are our terminal symbols. Cool. These are also terminals as well. Yeah. Okay. A derivation tree is also called a parse tree. You may see it written with the root at the bottom, so where we start with A here and then we do expand upwards, or with several edges instead of a triangle, which is how we did it earlier on, like this, where we just use edges and we didn't draw those triangles in. But they mean the same thing, and they're all parse trees. At the root, we always place the start symbol. So A is our start symbol. We always start there. We don't start with any of the other variables. And at each leaf, we have a terminal. Cool. Okay. So let's look at this example. The desired word appears by reading the leaves from left to right. So say we have this alphabet, and we have this grammar. This grammar accepts things like this. So the happy, tired, happy dog died, and the cat slept. Dinner ate a happy dog. So what this means is we can sort of create something that represents natural language using these context-free grammars. Would the brackets be a terminal symbol? Yeah, so the brackets would be a terminal symbol, just because it's we can't derive anything from a bracket. That is like a base case if we were doing this recursively. So all of our non-terminals in this grammar up here would be this set here. Sorry, all of our terminals would be this set here. I keep saying non-terminals. And our non-terminals would be A and B. So these are our non-terminals, and all of our terminals is everything that's not any of those variables. So all leaves. Yeah, so everything right at the bottom of the tree needs to be a terminal. If it's not a terminal, then we need to expand it from a non-terminal into another string of terminals and non-terminals until everything at the bottom is a terminal. Because if it's not a terminal, that means there's still some work to be done in terms of deriving something from it. Cool, okay. Let's try and write a derivation tree for... let's try this top one. Okay, so how could we go about writing a derivation tree? Where would we want to start? What's our... start symbol in the case of this grammar here. Okay, so our start symbol is whatever has an arrow next to it. Yeah, good. Okay, so S. Nice. Let's use a different colour. Okay, so we start with S. What does this become? There's only one rule that we can derive from S, and that's just C dot. These are technically two symbols, so I'll write it like this. C dot. Okay, this is a terminal, so this is done. This isn't a terminal, so what can we expand this C into? Or which one should we expand it into? Okay, so C, we can either go to NP-VP, or we can go to C and C. If we look at our sentence, we have something and something. So we want to use this rule here. So this would become C and C. So now we have a clause and a clause finished by a full stop. First clause is going to be everything before the answer. The happy, tired, happy dog died. We don't have any ands in here, so we know that for this C expansion, we want to use this NP-VP. So we can expand this into NP and VP. And we can do the same here because we've not got an and in that second one. Okay, so the NP here is going to be something in here. If we look at what NP actually expands to, article, noun, or dinner. There's no dinner here, so we know we're going to be using article noun. Art, N. Okay. An article is just a or the. We can see in this first half, our article is going to be the, so this can just be the. And this is a terminal, so that's this branch done. Okay, the, and then we have a noun. We know that it's not just dog or cat after the. We need to fit all of this in. So this is 3 adjectives. So we can make use of this. So we can say this noun expands to adjective, noun, adjective, noun, adjective, noun. Okay, so the happy, tired, happy, and this noun's just going to be dog. So what we can do is we can chain adjectives up like this, because noun just references itself with this rule here. So we could say the happy, tired, happy dog, and then VP is just going to be died. Well, we know we want to get died somehow, but we've got VP. So the only way we can get died is with this VI rule. So we want to say VP goes to VI, and VI is just died. Okay, so now we've got the happy, tired, happy dog died. So we've got up to here. We've also got our and from this. So now we just need to get the cat slept from these two. So does anyone want to talk me through how we'd get the cat slept from NP and VP? Or drop a message in chat. Okay, we've got a response. Got a few. Okay, NP to art N to the cat. Okay, so NP to art N, so that's expanding this here, and then art goes to the, and N goes to cat. Good. And then VP goes to, yep, VP we want to get slept from here, so from VP we need to go to VI, and then from VI we need to go to slept. Yep, good. And then we have our full stop here. Cool. Okay, so we've managed to derive this string with this grammar. So we'd say that this is in the grammar. And this would be the corresponding derivation tree. Awesome. Does that make sense to everyone, how we've sort of got this? Are there any questions about that? Okay. Feel free to ask anything if anyone's stuck. Okay. So, with context-free languages, if I can derive the same word. Yep. I think that comes up later on, but just we'll also discuss it now. So if you can derive the same word in 2 different ways with a grammar, we say that grammar is ambiguous. I think there's a good example later on, so when we get to that, if there's any questions, let me know. Okay, so context-free languages have something called the matching problem. So given a CFG, is the matching problem decidable? Is there some program that when given a word W over the alphabet, returns true if W is derivable, and false otherwise. The answer is yes. We have an algorithm of doing this, but it's not efficient. It has qubit complexity. So we can sort of derive whether a word is in a context-free grammar or not. There are efficient ways of solving this problem if we restrict our grammar to a set of rules. So when people design a grammar for a programming language, they'll try and design it to fit one of these special kinds. Just a few, I think this is some extension stuff, but it's quite interesting to know. A program that constructs a derivation tree for a given word is called a parser. Tools like Yak and Antler are parser generators. You can supply a grammar, and the tool will produce an efficient parser. Sounds like a next year thing. But anyway, designing context-free grammars. The following example, taken from SIPSA, recognize that name, showcases that in order to get the grammar for the language we first construct the grammar. Okay, let's just discuss what this language is. So 0n, 1n, given n is more than or equal to 0, union 1n, 0n, such that n is more than or equal to 0. Okay, so this is saying any word that has n ones and n zeros, or n zeros and n ones. As long as it has the same number of ones and zeros, and we're not mixing and matching. We have two separate sort of groups. Okay, so we first construct the grammar. S1 maps to 0, S11, or epsilon. And this is for the second language. So S2 maps to 1, S20, or epsilon. And if we think about it, this one, say we want to derive 000001111, or let's make it a bit shorter. Let's say we want to derive 0011 in this language. We can't, because we can say S1 maps to 01, S1, 01. And if we want to add more zeros and ones, we can just keep extending these S1s down and have as many zeros and ones as we want, and it will have the same number of zeros and ones. But if we don't want to expand anymore, we can just map this S1 to an epsilon, and that would be our terminal. And the same applies here. We can just expand 10, 10, 10, and have this as long as we want, or we can even just have an empty string. Okay. So if we want to work out the union of these two, this is all we have to do. We just have to create a new start symbol, have it mapped to one rule, and have it mapped to another rule. So both of these productions represent each individual language, and we're saying the start symbol is defined as anything in this language or anything in this language. For regular languages, the task of constructing equivalent context-free grammars is relatively easy. We can construct the DFA for the given language, and then convert the DFA into an equivalent context-free grammar. So how we can convert a DFA into a CFG is we can add rules for every single state. Create a variable Ri for each state Qi of the DFA. Add a rule Ri maps to a Rj for every transition function, and make R0 the variable of the grammar. Let's just talk through this and explain exactly what's going on here. So if we have these four states, we could say, for example, rule 1 is our start state. Just trying to think if that's what we want to do, actually. Yeah, okay. Rule 1 can be our start state. And this would map to B, R1, or A, R2. And the reason we've done that is because from 1, if we read in a B, we just end up at 1 again. And if we read in an A, we end up at 2. So let's define R2. R2 is defined as, from 2, if we read in an A, we go to 3. So A, R3, or B, R1. Okay, can anyone tell me what the rule will be for R3? Using the same sort of systematic method we're using. Okay, good, yeah. So from R3, sorry, A takes us to R3, so yeah, A, R3, or B takes us to 4, so B, R4. Good, and then finally R4 would just be A and B both take us to 4, so this would just be A, R4, or B, R4. And what we've done is we've represented this DFA as a Bacchus-Knorr form context-free grammar by just creating these rules and prepending the state transitions and the states together, just concatenating them together. So And then, yeah, we make R1 the start variable of the grammar, because this was our initial state in our initial DFA. Shouldn't you add an epsilon as there's no terminals? I mean, let's see. So if we had something like A, B, that should be accepted. So, oh yeah. Yeah, you're right. So all of our accepting states would also have an epsilon rule. Yeah, so the epsilon rule shows us that it's an accept state. Yeah, my bad. And that's this third step here. So we make all the variables corresponding to the states of the DFA. We add the rules using this pattern we've used where we say this is the transition which goes to this state. And then we've added the epsilon rule for all of our accept states. In this case, we only have 4 as an accept state, so we add the epsilon rule there. And then finally, we make our initial state the start state of the grammar. Awesome. Okay, moving on. We get the following grammar after the above steps, which is identical to the one we've got. Cool. Okay, given another grammar for arithmetic expressions, anytime this E symbol appears, an entire parentheses expression might appear recursively instead, because this T could go to this F could go to this bracketed E. Okay, I'm not entirely sure why they're highlighting this. In the above example, anytime he appears, to achieve this effect, place the variable symbol generating a structure in the location of the rules corresponding to it. Okay, I think it's just telling us that. Is there a reason E is bracketed? I don't think so. I think they're just trying to say we might have to take a bunch of steps just to go from E to this. So I'm guessing this is just saying there's probably better ways we can write this grammar out, because we're doing this recursively and we're passing E into T and we're passing T into F. Yeah. Okay, let's move on to the rest, and we can always see how that links in. Okay. Audio. Is there still audio? Can you guys still hear me? Okay, cool. I don't think we'll worry about that. Okay. This is quite an interesting one though. Give a context-free grammar for the set of palindromes over the alphabet AB. Oh, can you guys not hear me? Test. Okay, so let's say we had, we'll ignore this question 1 for now, but looking at question 2, give a context-free grammar for the set of palindromes over the alphabet AB. How could we do this? Let's try and think about this. Does anyone want to come up on stage and explain how we could create a CFG for palindromes over A and B? Any suggestions? Okay, so a set of palindromes. We want a start symbol, obviously. We need somewhere to define what's in our grammar. Oh, some people are typing. It would have rules like ASA, BSB. Yeah, okay, so we've got an example. So AS, I think you meant to put A here, but yeah. ASA or BSB or A or B or epsilon. Yeah, good Ollie. We want that epsilon rule as well. Okay, so this would say, this would accept an empty string. This would accept AA. It would accept ABB, ABBA, and it would accept a singleton. So this would accept a bunch of palindromes. If we try and think of anything that's not a palindrome, for example, AB would get rejected by this. I mean, I'd probably argue A and B are technically just palindromes because they're the same backwards as they are forwards. Yeah. So this is probably what I'd go with. Cool. Are there any questions about this CFG? Or any reasons why people might think it might not work? Last A equals terminal is allowed. Oh, right, yeah, okay, cool. Let's move on. Okay, so ambiguity. We did discuss this briefly, but if we can have more than one derivation tree from several different derivations, if we can have more than one derivation tree, then we say that a grammar is ambiguous. For example, this equation here as defined by this language, 3 plus 5 times 3, can either be we do the plus first and then we do the times, or we do the times first and then we do the plus. So there's two ways of deriving this, and this creates ambiguity. The above grammar doesn't take into account the order of precedence of operators, so it doesn't ensure that we always times before we plus, like we would in conventional maths, BOD maths. In contrast, the following grammar generates exactly the same language, but here everything has a unique derivation tree. So this grammar is unambiguous, whereas the one above is ambiguous. So this takes into account the precedence. It means if we have something like A plus B or B, and we have this being a multiplication, let's try and derive our 3 plus 5 times 3 again, but with this one. So we want to derive 3 plus 5 times 3. Here, we're forced into expanding this into B, because we can't... we're forced in expanding this to this first thing here, because this is not anything times anything. So what we'd have to do is we'd have to say something like... We'd have to expand this into something like A plus B. A becomes 3, and B becomes B times C. This becomes 3, and this becomes 5. This becomes C, which becomes 5. Okay, so here we're forced to do the multiplication first, technically. Like, it's more specific than the plus. Whereas before, we could have two trees, but here we won't be able to have the times up here in any way. So this removes that ambiguity. There's only one way to derive any word in this grammar. You might think, can we tell whether a grammar is ambiguous or not? We can't. That's actually an undecidable property on context-free grammars. But we don't need to know the proof for that. Okay. Let's have a go at this. How can we show that this is ambiguous? How can we show that this grammar here is ambiguous over the alphabet AB? I'm showing there's two ways to get it. Okay, let's just try and think of two examples which we can use to show this is ambiguous. Okay, we've got quite a few suggestions in chat. So you could derive AAA in two ways. Okay, let's look at this. So if you want to derive AAA in two ways, so we can either start with P and say something like QA, where Q becomes AAP and P becomes epsilon. So this is one way of deriving AAA. Okay, and then another way is if we do AQ. So if we do P, do the A here, we do the Q here. Q becomes A, P, epsilon. Okay, so here we've derived this in this order, and here we've derived it in this order. So we've got two derivation trees, which means this grammar is ambiguous. Cool. Okay. Let's move on. Chomsky normal form. Okay, so Chomsky normal form is a special type of context-free grammar, and it only allows these types of rules. So we can have A, which maps to any two non-terminal symbols, or we can have it mapped to a single terminal symbol. So one other thing we can have is we can have the start symbol mapped to epsilon, but only the start symbol, no other symbols. Chomsky normal form has various uses, but one noteworthy one is that a derivation of a non-empty word involves 2n minus 1 steps. And so it kind of means we can always derive a word in a certain number of steps, where n is the word's length. Okay, so let's say we want to convert this CFG into CNF. Okay, one sec, let's just look at the chat. Is ambiguity of a context-free grammar a semi-decidable property? What about non-ambiguity? Okay. Okay, let's move on to Chomsky normal form. So if we have this grammar, this context-free grammar, how we can convert it into Chomsky is we can create this start variable s0, which just maps to the old start variable. Then we remove any epsilon rules that aren't in the start variable. So in this case, b had an epsilon rule, so we get rid of that. And what we do is anywhere where there was a reference to b, we add or epsilon. So in this case, we had ab, which would just be or a, because in the event that b is an epsilon, it would just be a. Here, in the event that b is an epsilon, it would just be an epsilon. Then we remove the epsilon rule in a, so we get rid of that. And now here we could also have SA if this first one's an epsilon. We could have AS if this second one's an epsilon. I believe that's all we'd need to do there. Then we want to remove unit rules. So something which just goes to another variable. So here we have S going to itself. All we do there is we just add all the rules here to the end of S. Because S already has those rules, we don't need to add them again. Remove the unit rule S0 to S. So even the start variable can't go to another variable if it's just a unit rule. So we've got rid of this by just copying all of this up here, and we get this. Remove the unit rule A maps to B, so removing this rule here. And to do that, we just replace this B with whatever the B rule is defined as. Remove the unit rule A maps to S, so remove this rule here by just copying everything in S and sticking it into A. And then we can just, we keep doing these steps. We just add a rule for AS or SA or whatnot. We can add a rule for AS or SA, like C maps to SA, just so that everything is at most, everything is just 2 variables, because we can't have this mapping to 3 variables. And replace all of these with AC. D just maps to a terminal A, B just maps to a terminal B, because we're not allowed to do this. We're not allowed to mix a terminal and a non-terminal. So we have to make this a variable. And in the same way, we have to make this a variable. I'm not entirely sure why we'd need to make this a variable. Oh, right, okay, yeah. So obviously if we... That was already there, yeah. So they've just made this D as an A so that we can use that in these pairs. Okay. We'll just discuss these two and then have a go at this and discuss that question. Okay, emptiness and fullness. To test whether a CFG accepts some word, we mark each variable that is able to turn a word, that is able to turn into a word. So A maps to this. We know these can turn into a word. If these can turn into a word, then so can this. And we just recursively test if each rule can be turned into some word. Can we test whether the CFG accepts every word over the given alphabet? No, this is undecidable. We don't need to know the proof for that again. Beyond context-free languages, not all languages are context-free because there's uncountably many languages, yet countably many CFGs because there's a finite set of symbols we can use to represent CFGs. Yeah, okay. Let's have a go at this question here. So, test our understanding. Convert the following CFG into an equivalent context-free grammar in Chomsky normal form. So, let me find some space. Okay. This question here. I'll give us a moment to talk through it, maybe write out some solutions, or what's the first step we'd take. Okay, so we've got a suggestion to add a new start variable. Good. Okay, so let's say this is our start variable. What do we want this to map to? S0 equals final updated A. Okay, let's map this to A. And then let's bring down our rules from before. So we had BAB or B or epsilon. And then for B, we had 0, 0 or epsilon. Okay, we want to get rid of all the epsilon rules. So let's get rid of this epsilon rule first. If we got rid of this, we'd have S maps to A, we'd have A maps to BAB or B or epsilon, B maps to, I'm going to copy this down actually, I think that'll be the fastest way of doing this. Okay, so if we copy this, okay, so we want to get rid of this epsilon rule. So if we get rid of that epsilon rule, all of a sudden, this could be epsilon. We've already accounted for that it could be epsilon. So we can get rid of this rule, and and we need to add some rules. We need to say, okay, this could even just be AB, or it could be BA, because if either of these are epsilons, then we want to consider that. Or it could even just be A if both of these B's derive to epsilons. A, B, B, A, or A. Yeah, perfect. We wouldn't... Oh, yeah, good point, Ollie. We would actually need that B rule as well. So we'd actually want to keep that rule. In the event that this... Wait, would we? I don't think we would need that B rule. Yeah, no. Yeah, you would. You need B because you have the 0, 0. This rule here. Oh, right, because that was... Yeah, because that was there before. Yeah. Yeah, no, that makes sense. My bad. Okay, so we have this grammar here. Right, so... Let's just make this all black. Get rid of this. Okay, so now we have this. We want to get rid of this epsilon rule. So we delete. We add... Wait, let's think about the order we want to do this. Remove epsilon from A, you get BB. Cool. So this would mean we have a new rule, BB. Okay. And anywhere we represented an A, this could possibly be an epsilon. And I don't believe we need to do anything else there. Cool. Okay. Now, let's remove the unit rules. So, in terms of our unit rules, we want to... Let's make all this... Right. We want to get rid of things like S maps to A maps to B, A maps to A. Okay, so in order to get rid of them, we just have to copy the rules across. So, yeah, this is terminal. So we'd also need to do something about that later on, because 0 is a single terminal symbol on its own. A to A can just be deleted, right? It can, yeah, good. So we can just get rid of that rule there. Let me... Okay. Bring up all of A to S. Good, yeah, so we want to replace this A rule with BAB, or B, or AB, or BA, or BB. Okay. And then we still have an A to B unit rule, so we want to get rid of that one. Let's do that in another step. Okay, so all our epsilon rules are removed. We've only got an epsilon in the start, and that's fine. Okay, let's remove this epsilon rule first. So get rid of A maps to B. Now we want to copy B's definition into here. So 0, 0. We also want to do the same here. This also can now go to 0, 0. And finally, we've got rid of all the unit rules. We've got rid of all of the epsilons in the rules they can't be in. Now, all we have to do is we just have to clear up the stuff mapping to 0, 0, because we can't have things mapping to 2. Okay, I do not know what's happened there. Okay, right, so BAB. Right, so let's first sort out B, because we know this can't map to 2 terminals. Let's say C is a new rule, which is just 0. Then we can say B just becomes CC, because we're allowed to do this with 2 variables. How do we get epsilon at S? When we replace the A rule up here, when we copied this across, because if we get rid of this epsilon rule, this could be or epsilon, basically. Yeah. Right, so this is valid now. This is valid. Working backwards, this isn't valid. So let's make a new rule called D, maps to say BA, because now BAB can just become DB. Same here. And we have a valid, no, not yet. Okay, and then we also want these 0, 0s to map to that B. But we can't have this, so we could either make this 0, 0, or we could just make this map to CC, like this. Cool. BA becomes D2, or is that unnecessary? What do you mean? Oh, right, no, because then it would be 1 maps to 1 thing. We need it to map to 2 things. Cool. Okay, so this would be our final CNF. Does that make sense? Awesome.